Our galaxy is doomed. We are hurtling toward a collision that will destroy everything we've known in the night sky. At least, that's what we were told for decades. But what if it never actually happens? The Milky Way, a massive spiral of hundreds of billions of suns, is speeding through space at about 70 miles per second toward the Andromeda Galaxy. Andromeda, also known as M31, is nearly identical in mass and shape to the Milky Way and is our largest cosmic neighbor. For a long time, a dramatic prediction was accepted as true. In about 4 billion years, these two giant spirals would collide head-on, destroying their familiar shapes and merging into one elliptical galaxy, often dubbed Milkdromeda. This was presented as a certainty, a fate as inevitable as gravity itself. However, new measurements from the Hubble and Gaia telescopes, along with previously overlooked gravitational effects from smaller companion galaxies, now point to a radically different future. The once inevitable collision may not be so inevitable after all. In 2012, measurements from the Hubble Space Telescope provided the first clear picture of Andromeda's motion. Hubble data showed that Andromeda's sideways or tangential motion across the sky was very small, less than 0.1 milliarc seconds per year. In other words, Andromeda was moving almost directly toward the Milky Way. Combined with its known approach speed of 70 miles per second, determined by its blue-shifted light, this suggested an almost direct collision course. At the time, models predicted that the galaxies would begin merging in about 4 to 5 billion years. The night skies from Earth's future were imagined in breathtaking illustrations. Andromeda swelling and filling the sky, tidal forces twisting the Milky Way's spiral arms. Eventually, the stellar disk of both galaxies would blend and form a new giant galaxy with a diffuse ellipsoid shape and a cosmic pile of stars known as an elliptical galaxy. This merged galaxy was expected to dominate the remnants of the local group, a cluster of about 100 galaxies that includes both of ours. The predicted merger even made its way into textbooks as virtually unavoidable, often under the playful name Milkdromeda. Yet science often advances by overturning its own certainties. Even as this scenario gained popularity, astronomers continued refining their measurements. Small errors in Andromeda's velocity left room for doubt. Could it be moving sideways, slightly more than Hubble's early measurements suggested? If so, the future clash might not be a head-on collision. Hints of this emerged a few years ago. Preliminary analysis from the Gaia Space Observatory indicated that Andromeda's actual trajectory might be angular enough to avoid a direct collision. Moreover, researchers began to realize that the gravitational influence of other nearby galaxies could subtly nudge the Milky Way Andromeda system. The original forecast treated the collision as a simple two-body problem, but in reality, our galactic neighborhood is more densely populated and complex. The stage was set for a scientific mystery. Is the Milky Way truly doomed to collide with Andromeda, or could it somehow avoid this fate? One of the main suspects in this galactic detective story is the Large Magellanic Cloud, LMC. The LMC is a dwarf satellite galaxy currently orbiting the Milky Way. It's much smaller than Andromeda or the Milky Way, but still quite massive, about 10 to 20% of the Milky Way's mass. For years, future collision simulations didn't factor in the LMC's influence. It was assumed to be too minor to affect the titanic Milky Way-Andromeda pair. Dr. Til Sawala,
an astrophysicist from the University of Helsinki,
notes that early studies only considered the most likely value for each variable, and often left out players like the LMC. But the new data shows that the LMC isn't just a passive observer. It's speeding toward the Milky Way itself, and its gravity is tugging at the outskirts of our galaxy. In fact, Sawala's team found that the LMC's pull, directed perpendicular to the line of approach between the Milky Way and Andromeda, is strong enough to significantly alter the Milky Way's path. Its gravitational pull, directed perpendicular to the orbit with Andromeda, perturbs the Milky Way's motion enough to significantly reduce the chance of a merger, Sawala explains. In essence, the LMC may be nudging the Milky Way slightly off its previously projected collision course. Another participant in this cosmic interaction is M33, the Triangulum Galaxy. M33 is the third largest in the local group, a spiral galaxy about half the size of the Milky Way. Earlier studies accounted for M33's gravity and found that it actually increased the likelihood of a merger with Andromeda as M33 pulls both galaxies together. Sawala's new work confirms this, including just Triangulum M33 makes a collision more likely. But including both M33 and the LMC has the opposite effect. The perpendicular gravitational pull of the LMC dominates, reducing the overall likelihood of a collision. It's a bit like two celestial currents influencing a drifting ship. One current pushes it toward a collision, while the other deflects it off course. The final outcome depends on the relative strength and direction of those forces. Crucially, scientists also realize that uncertainties in the observables, the current positions, velocities, and masses of all these galaxies, could lead to vastly different future outcomes. Even slight errors in Andromeda's tangential velocity or the Milky Way's mass create butterfly effect variations across billions of years. The only way to understand this uncertainty is to embrace it, to run a large number of simulations, each with slightly different initial conditions within the allowable observational ranges, and see what results are possible.
That's exactly what a team of scientists from Helsinki, Durham, and Toulouse set out to do in a new study published in Nature Astronomy in 2025.
To determine the fate of the Milky Way, the researchers ran a series of 100,000 simulated future scenarios. Each simulation forecasted the movements of the Milky Way, Andromeda, M33, and the LMC over the next 10 billion years. It's important to note that they didn't rely on a single best guess set of parameters. Instead, they varied key factors across their full range of uncertainty. 22 different variables in total, according to the study. These included the current velocities of the galaxies, with Andromeda's exact tangential velocity remaining critically uncertain, the distances and the masses of each galaxy's dark matter halo, since mass affects gravitational pull. The simulations also accounted for dynamical friction, the drag-like resistance that occurs when the dark matter halos of galaxies interact, gradually draining orbital energy and possibly leading to a merger over time. By conducting so many trials, the scientists effectively explored a space of possibilities far greater than that of any previous study. A decisive factor was the inclusion of Gaia satellite data alongside Hubble's measurements. Gaia is mapping the positions and movements of stars with unprecedented precision, helping to determine the Milky Way's own motion and offering hints about Andromeda's sideways motion, even though measuring Andromeda's proper motion is extremely difficult due to its vast distance. Meanwhile, revised mass estimates, about 1 trillion solar masses for the Milky Way, similar values for Andromeda, and lower values for M33 and the LMC, were all used to update the gravitational models. Using all this data, the team's supercomputer at Durham University ran one scenario after another, each representing a possible future of the local group. After thousands upon thousands of simulated universes, a striking picture emerged. The once inevitable collision was no longer guaranteed. Instead of one fate, there appeared a spectrum of outcomes, from head-on collisions to glancing blows and near misses, each with a certain probability based on what we currently know. When the dust settled from those 100,000 simulations, the researchers calculated how often each general outcome occurred. The future of the Milky Way and Andromeda appeared to fall into three broad categories. The first, possibly, is a direct head-on collision in approximately 4 to 5 billion years, the probability of which is about 2%. Only 2% of the simulations resulted in the originally dramatic scenario happening on schedule. In these rare cases, the galaxies collided almost directly with each other in about 5 billion years or less, merging quickly after a single pass. This is essentially the bullseye outcome that early Hubble studies predicted as the likely fate. If this happens around the time the Sun is 5 billion years older, the two disks will catastrophically collide and begin to merge, completely destroying the majestic spiral structures of both galaxies. A new elliptical galaxy would form from the wreckage. However, the fact that this only occurred in 2% of cases means that, based on current data, this outcome is extremely unlikely. The second category of outcomes involves an eventual merger following a close pass, taking 7 to 10 billion years, with a probability of about 48%. That means nearly half the scenarios end in a merger, but not after the first encounter and not on the rapid timeline previously assumed. Instead, these are slow-motion mergers. Typically, the galaxies pass close to one another, perhaps a few 100,000 light-years apart, strongly disrupting their structures. Tidal forces stretch their spiral arms and trigger new star formation. But they don't cause an immediate merger. After that first close approach, they drift apart again. Over billions of years, dynamical friction saps energy from their relative motion. They orbit one another on a decaying trajectory, ultimately merging after 8 to 10 billion years. In these cases, the final merger occurs much later than previously believed, about as long from now as the universe has already existed. And by then, interestingly, our sun will be long dead. It will have burned through its fuel and likely become a white dwarf in 7 to 8 billion years. So any observers on Earth would already be gone or vastly different. These prolonged mergers aren't as neat as a direct collision. They may involve multiple passes and a more chaotic mixing of stars, but in the end they still result in a single merged galaxy. This category represents a significant possibility, suggesting that a slow merger is a real contender for our galaxy's fate. The third category involves results where no collision takes place for at least 10 billion years, a probability of about 50%. And amazingly, the remaining half of all simulations did not result in a merge within the next 10 billion years. In these scenarios, the Milky Way and Andromeda pass by one another without colliding. They may have one or more distant encounters, such as flying past each other at a distance of about 1 million light-years, which is a near miss by cosmic standards, but they never get much closer than that. At such distances, the gravitational drag between them is too weak to pull them together. In these cases, the Milky Way and Andromeda may orbit loosely around each other or drift apart very slowly, potentially taking 20 to 30 billion years or more to ever merge, if they merge at all. Practically speaking, this means that there would be no dramatic structural changes to either galaxy in the foreseeable future. They would continue evolving largely unchanged for a very long time, retaining their spiral forms. What tips the scales between these different future outcomes? The key players are the previously mentioned Large Magellanic Cloud, LMC, and the Triangulum Galaxy, M33. Simulations show that ignoring these smaller galaxies and their associated uncertainties leads to the old conclusion: a rapid collision between the Milky Way and Andromeda. But once they're factored in, the picture changes dramatically. In simulations where M33 Triangulum was added to the two-galaxy system without the LMC, the probability of collision actually increased. The additional gravity from M33 acts like a lever, drawing the Milky Way and Andromeda closer. In fact, Andromeda and M33 are already in a slow gravitational interaction. M33 orbits Andromeda, and the mass of M33 enhances the pull, drawing Andromeda towards us. In contrast, the influence of the LMC proves to be a disruptive factor. Its orbit around the Milky Way is nearly perpendicular to the Milky Way-Andromeda line, giving it a sideways nudge. Essentially, the LMC is pulling the Milky Way slightly in a different direction. Not enough to completely knock us off course, but enough in many cases to turn a direct hit into a glancing blow, or a glancing blow into a clean miss. There's also the intriguing possibility that the Milky Way will merge with the LMC long before it ever meets Andromeda. The study concluded that a Milky Way LMC merger is almost certain within the next 2 billion years. The LMC, being much lighter, will be absorbed by our galaxy. In fact, signs of its final demise may already be visible in the disturbances along the Milky Way's outer edges. If, or rather when, the LMC merges with the Milky Way's disk and halo, it'll transfer its mass, both stars and dark matter, to the Milky Way. This could make the Milky Way more massive and slightly shift its center of gravity, factors that could further influence its later interaction with Andromeda. Current simulations include this process and still find many outcomes in which Andromeda never fully merges with the Milky Way. Meanwhile, Triangulum M33 may ultimately be drawn into the merger as well. In some scenarios, M33 might first merge with Andromeda and then join the newly formed system that results from the slow merger of the Milky Way and Andromeda. The interaction's complex. 4 substantial galaxies, 2 large and 2 smaller ones, are moving within the gravitational potential field of the local group. The pull of the LMC and the uncertainty in Andromeda's motion vector mean that in this case, a cosmic catastrophe is not inevitable. What would each of these scenarios mean for the cosmic structures we know and for our solar system? Well, it's important to emphasize that galactic collisions are not like car crashes or Hollywood-style explosions. Galaxies are mostly made up of empty space. Even in a head-on collision, actual star or planet collisions are extremely unlikely. Instead, stars and planetary systems would simply begin to move under new gravitational influences. In fact, simulations show that the probability of any stars actually colliding during the Milky Way-Andromeda merger is virtually zero. Earth, if it still exists and is habitable at the time, might not feel the effects of the collision in any catastrophic way. Our solar system could continue orbiting safely within the newly merged galaxy, or it might drift into intergalactic space, experiencing no local disruptions. Either way, humanity, or whatever descendants of life may exist by then, will almost certainly have already found a new home, regardless of galactic events. One event that will eventually occur in the merger scenario is the fusion of the central supermassive black holes of the two galaxies. After the merger, the Milky Way's central black hole, Sagittarius A, about 4 million solar masses, and Andromeda's black hole, a monster at around 100 million solar masses, will sink toward the center of the new galaxy, spiraling together due to dynamical friction, and ultimately merge into an even larger black hole. Such a colossal black hole merger would release massive bursts of gravitational waves and may temporarily turn the new galactic core into an active quasar as gas is drawn in. These phenomena could light up the entire sky of the merged galaxy. Additionally, colliding gas clouds could trigger waves of a new star formation and supernovae. However, since our solar system is far from the galactic center, it wouldn't be directly affected by the radiation flash, apart from perhaps some extra high energy cosmic rays. Nothing life on Earth at that time would likely notice. So, the mystery remains. Will the Milky Way and Andromeda actually collide and merge, or will they just pass by one another? The question is still far from settled. Astronomers eagerly await new data that could further narrow down its trajectory, especially fresh Gaia measurements of Andromeda's motion. For now, we continue racing toward our neighbor at about 250,000 miles per hour. And we're reminded once again that great cosmic truths can change quickly with new data. The future of the Milky Way is not a pre-written script of cosmic doom. It's an unfolding story that we are only beginning to understand, and that future generations of astronomers will continue to watch with awe and curiosity.